Okay, so today we will discuss the P1 and P2 both. And for P1, we have autoregressive language modeling with the causal transformer decoder. So we'll go through some logistics, objectives, setup. Then introduction of some concepts that are covered. And then we have two tasks for this homework for P1. So we'll go through them one by one. So these are some important dates. The homework was released yesterday night. The early deadline is November 21st, and it's due December 5. Is that?
That's the latest that we can do, like with all this time.
Yeah.
But I think the month very.
Okay. So this assignment is significantly more challenging than the previous ones. I know we say this every assignment, but yeah. So we recommend starting early, and please reach out and attend office hours if you get stuck. So for the materials, you have the PDF for the write-up. You have a zip file. That's the ideal homework for zip file for and that handout is to be used for both the homework parts, so part 1 and part 2. And then you have a starter notebook specifically for homework for P1. So all these materials are on Autolab. Okay, so in this part, you'll implement self-attention from scratch. So in self-attention, you'll implement the scale dot product attention and the multi-head attention. And we'll also understand the fundamentals of language modeling, so including next token prediction and the full sequence generation. You'll implement positional encoding, and finally, like you'll learn how to apply causal and padding masks to enforce the autoregressive behavior and how to handle variable length inputs and dealing with like unlabeled data. So you'll also explore multi-head attention. Uh, you'll write from scratch in this homework all the self-attention layers, feed-forward networks, and full decoder layers. And then finally, in homework for P1 itself, you'll train the causal transformer decoder model for the text generation tasks. So just a setup and workflow of this homework. So there is a test suite that we have provided to you, which is very detailed, and you'll be able to test subparts of this homework individually. Then we also provide a subset of the data set so that you can just test everything locally first, and you don't need to like train on a full data set at once. So also like this assignment provides you how, like it gives you an opportunity how to develop end-to-end deep learning pipelines from scratch. So it will be more, it will be closer to the real world research projects that you do as compared to like the previous assignments. Okay, so please download this ideal homework for handout, and this is how the handout directory should look like. There would be a homework for dataset, the library. So here you'll be implementing all the code for self-attention, multi-head attention. This is your MyTorch library, where you'll be adding more parts to your incrementally developing MyTorch, and then some tests. And also, this is a note, this is a reason of a lot of errors that we see, that your notebook should be in the current working directory, which is this one. Uh, sorry, your notebook's current working directory should be the same as the handout directory, which is this one. Okay, so this is just how your data set will look like. So for homework for P1, it's just these files. This is your main homework for library, and this is a combination of the files that you'll be implementing as part of homework for P1 and P2. So it is your responsibility to ensure that the implementations are consistent for both the homeworks, because some parts in homework for P2 would be using some implementations from P1 as well. So there will be a little bit of engineering effort here as well that you'll be expected to put in. So this is just like a description of the P1s and P2s. We'll touch more on this moving ahead. Yeah, so in your MyTorch, you'll be adding multi-head attention and scale dot product attention in this homework. And these are just tests. Okay, so coming to language modeling. So in this homework, what is language modeling? It is modeling the probability distribution of symbol sequences in a language and generating sequences from this distribution. So now a question also comes that how do we define language? So a language is defined as a set of all valid sequences of symbols from a vocabulary. So if you're dealing with characters, then all your vocabulary would be characters and your language will be all possible sequences of those characters and so on. So we simplify this problem by using the Bayes rule, and we try to condition the probability of the next token based on the previously produced tokens in this format. So there's also a very nice preamble section given in the write-up. So on page 8, please go through it carefully before starting the homework. Okay, coming to the architecture, this is the difference between the P1 and P2. So on the left, you see the decoder-only transformer. This is what you would be implementing in this homework. This is based on GPT-2 that was a foundation for GPT-4 and many other models. And yeah, so in P1, we'll be only implementing the decoder layers. So this is just a little detail about that. And this is the same how the training objective basically. So how after training, we finally expect our model to be able to predict, to be able to generate my next tokens based on the previous tokens. So we use self-supervision here. Every token predicts the next token. And so the model is able to learn the next tokens without manual labels. So like SOS, EOS, these will all be part of our vocabulary. And every token will predict the next token. So SOS will predict I will predict SWAM, and so on. So we talk a lot about token embeddings. We have been talking about it in lectures in detail, in labs, and in this homework also, you'll get to deal with them on actual data. So each token in the input sequence, that's x1 to xn, let's say, belongs to 1 to k. So 1 to k is my vocabulary size. So from my vocabulary, some tokens, which are in my input sequence, they all will be converted to a sequence of d-dimensional embedding vectors. So this is my embedding vector, and this is just implemented using the PyTorch embedding function. And finally, when we get the d-dimensional embedding vector, we inject these with positional encodings. So I'm sure you have learned positional encodings in detail, how we add positional encodings to model the relationships between different words in the input sequence, and then pass them through the decoder layer finally. So my model as an output will produce H1 to Hn hidden states. Each will be of the dimensionality. And finally, like our goal would be to obtain logits over the vocabulary K. So we will apply this linear transformation. Yep. Okay, so we can apply softmax to obtain the final probabilities. However, we use PyTorch's implementation of cross-entropy loss, which takes the raw logits Y and the ground truth token sequence and internally applies the log softmax and the negative log likelihood before computing the loss. So we would be just using that in this homework.
All right, cool. Thanks for that introduction. Now we're going to get into the main tasks of the homework. So as you may have guessed from our recent recitations, labs, and what we're doing in class, we're going to be implementing an initial or naive version of the transformer architecture. So we say transformers and it's analogous to this term attention, but is it a new concept and where has it come from? So it's actually not that recent and it's been around in different forms for over 10 years now. It started back in the field of natural language processing in 2014 with Pardano attention, then Luong attention. For a while, these were the most useful and they all shared the same idea of weighing your input samples with respect to what you're decoding at a certain timestamp. However, attention really kicked off with the introduction of the transformer architecture, which is what we'll be implementing this homework. And this form of attention is known as QKV attention, query, key, and value attention. In the same paper, multi-head attention was also introduced, and multi-head attention is what almost all implementations nowadays use because it has shown subtle but important performance gains compared to single-head attention. Beyond this, there are variations known as self-attention and cross-attention that you'll figure out through programming in PyTorch. All right, so task one, as we said, we're going to be implementing the most basic QKV attention known as scaled dot product attention. Overall, this is what the workflow looks like. You have a Q vector, K vector, and V vector. You do a matrix multiplication of your K and Q vectors, scale them by a certain scaling factor. In our root, it's under root dimensionality of the K vector. Then we mask to ensure our training paradigm. Say, we'll find out in this homework how we train these transformer models. A popular method to train them is next token prediction. And the mask is crucial in allowing us to enable this formulation of next token prediction. We'll see how later on. After that, this final score goes into your softmax, which is an activation function we've been seeing since the start of class. That generates what we know as attention scores. Finally, with those attention scores, we multiply them with the value vector or value matrix in the event of multiple tokens, and that's how we get our context vector. Multi-head attention is a very simple extension of this idea. Instead of taking the entire QKV vectors and doing one forward pass operation, we split our QKV matrices into smaller matrices and perform scale dot product attention for each one of these subset of K, Q, V vectors, and finally concatenate them at the end. So this concatenation step is honestly the only major difference between multi-head attention and scale dot product attention. So I've always gone on about QKV, but what do they actually look like? And I'd encourage you as we implement this homework to always think about dimensions. It's very important to know the sequence length, that is the length of the tokens in your input, the dimensionality of the embeddings that you're dealing with, and overall what your matrices look like at every step of processing. So here, T is our number of tokens, D is the dimensionality of your query vector, K transpose has D as the first value, sorry, not first value, first dimension, and T, which is again the number of tokens. Together, when you multiply this as QK transpose, then you end up with a matrix that's of dimension T cross T, which is referred to as our attention map. All right, so let's talk a little bit more about the implementation. So as you saw, it's rather straightforward in the sense that we're just taking linear layers, doing various operations with them, actually taking multiple linear layers and combining them in specific ways. So to get started, we will be implementing a very generic linear class to handle an input that will be A of shape anything, comma, in features. We'll quickly take a look at this in code. As you can see, it's very similar to what you've done in homework 1. And all we're going to be doing now is extending it to a Oh, okay. It says, do I share the entire window now?
Yeah, just share this. Sorry.
Thanks. All right, cool. So we will be again implementing a linear layer, which is very similar to what you did in homework 1, but we'll just be making it more general for different sized inputs. So the basic steps are as follows. We flatten the input tensor to a 2D matrix of shape, batch size, comma, and features. We perform our affine transformation, which is multiplying by the weight, adding the bias, and then passing it through the nonlinearity. Then we simply unflatten back to the original dimensions. Again, always pay attention to dimensions when you're dealing with matrices. You must have got a ring of that throughout all of these homeworks. Again, we strongly recommend that you incrementally test your approach to a subsection before moving on, because everything builds upon what you've implemented previously. So that will cover the forward function, but what about the backward pass? Again, very similar to what you've already done. We reshape the 2D gradient of shape, batch size, comma, out features. Then we reshape the stored input tensor to the specific shape. We compute the gradient of the loss with respect to the input following these equations here. Lastly, we reshape back to the original input size. Again, matching sizes as we go on. That will all be implemented in the backward function over here. Next is the softmax operation. We saw this previously, that we do softmax after computing QK transpose divided by our scalar. Again, very similar to what you've done previously. We have an init, we have a forward, we have a backward. So for forward, it's well, yeah, you're aware of what we do. We just take the exponent. But when we talk about backward, we look at all the input values Z and probabilities that come from the softmax, which will denote as lowercase a, which represent the attention scores. We compute the gradient by right multiplying the loss with respect to these affine values with the Jacobian. So this is the loss with respect to those attention scores, and this is a Jacobian. The final gradient tensor will have the same shape as your input tensor, again, simply matching dimensions. And this is a helpful function. It's also mentioned in the write-up, but np.moveAxis will allow you to do basically tensor manipulation. All of this will fit in your backward function here. Okay, now we come on to the meat of it. So do you have a question? Are there any questions? All right. Are there any questions on Zoom, or is it fine till now? Cool. All right, now we'll talk about the meat of what we're implementing, which is scale dot product detention. As you said, it takes on this form here, where Q is our query vector, K are our keys. The under root dk is the scaling factor that we talk about. Dk is the dimension of our key vector, and under root is just a constant or a function chosen that also monotonically increases with the increase in the dimensionality of k. It's just used for the sake of scaling, and scaling is important when we're passing into the softmax, because the softmax squishes your values into a range between 0 and 1. That's why we don't want the value inside the softmax to be very high, because it'll all be squished to 1, or we don't want it to be very low, otherwise it'll all be squished to 0, which is why we have the scaling factor here. Yeah, so take a look at these dimensions. The query matrix Q will have shape n, comma, whatever comes in the middle, HLE, where H is the number of attention heads for the key n value. L is the length of the target sequence. As I said, input tokens, output tokens. And E is the embedding dimension. So this will probably come from your tokenizer. Yeah, we do a similar thing for K as well. K will have the same embedding dimension as the query. However, that need not be possible, or need not be the same for the value matrix. Here you can have a different embedding dimension that we're denoting by EV. Optionally, we'll also have a Boolean mask matrix M of this shape, and this matrix M, as I said earlier, helps us enforce next token prediction. Okay, cool. So ultimately, this is the function you will be implementing, this class, sorry. It also is simple. It just has a forward and backward. And the forward, the backward looks a little bit like this. The loss with respect to the value vector is your attention map score transposed times the the derivative of the loss with respect to the output. Similarly, we calculate the gradient with respect to the attention scores A. Again, you simply multiply with your value vector the gradient with respect to the scale dot product scale dot product value is the softmax backward of dl by dA, so on and so forth for Q and K. You guys must have seen this all before. Again, note this scaling factor over here. Yeah. Cool. So that covers our forward and backward over here. Not much is given to you to start out with, but do follow the comments and keep checking your dimensions. Oh, because of the black. Oh. Thanks. Cool. I mean, until now, it's been rather straightforward. We always have a forward and a backward. Not much is given in terms of prior implementation, but remember to match matrix dimensions. Okay, that's half of task one, which was scaled up our attention. And now we're going to move from SDPA to multi-head attention. As I said earlier, it's only a small tweak. We're essentially dividing up this attention operation across multiple transformer heads. Overall, it looks something like this, where previously we just had one attention head, we split it up, then we perform attention on that subset of the vector across all heads, then we concatenate them across all the rows, and then we have to mix these concatenated features. We do that through one linear layer, and that's how we get the combined hidden states. So we'll quickly walk through the pseudocode here. We'll project our query key value matrices using linear layers, as we would have done for scale dot product attention. We implement the split heads class, which creates the number of attention heads. I would encourage you guys to think about the value we can give to the number of attention heads. Can it be arbitrary? Say my number of input tokens was 32. Can I arbitrarily give number of attention heads as 15? Is there any relation between the input token dimensions and the number of attention heads? The answer is yes, but I encourage you guys to think about that. And you'll definitely see this when you implement it. Then we implement the merge masks function to merge the key padding mask and the attention mask into a single mask. We'll go over that in the pseudocode, in the starter code. Then we apply scaled operator attention to each individual head, as you saw in the diagram on the previous slide. Then we implement concat head to merge the outputs from each of these heads, follow that up with a linear layer, and then we move on to the next block. So in code, this is what it looks like. We have to start out by initializing our scale dot product attention layers as well as our linear layers. Again here, the only important thing to look forward to are the matrix dimensions. We initialize weights, don't touch this. Then we go to forward. Again, we first compute the query keys and values. Then we split the query key and value into multiple heads. So the answer to the question I asked is in this comment here, where you basically split along the embedding dimension. And notice here, we actually want number of heads to be a factor of embedding dimension. We cannot arbitrarily choose a specific value for number of attention heads. Here we merge the masks that we've generated. So there'll be two masks here. One mask matrix will be for the next token prediction task, which essentially masks out the subsequent tokens that the transformer has to predict in an autoregressive manner. And the other the other mask is simply to mask out all the padding tokens that we're using. Then we apply the attention mechanism, merge the attention outputs, and then we do projection. Projection is the linear layer that we spoke about. So that is our forward pass. Again, it looks like a lot of steps, but they're mostly just a few lines each. Now we'll look at the backward pass. We backpropagate through the output projection using the gradient of the loss with respect to the output. So as we've done previously, and this is very similar with scale dot product attention. The important part here is splitting the gradients into multiple heads using the split heads method. We then backpropagate the gradients through the scaled dot product attention for each head. We merge the heads of gradients for the query key value using concat heads, which is another function that's defined for you. Then we backpropagate these gradients through input projections. Again, these are the functions we spoke about in the pseudocode. For example, merge masks. As you saw, why we want to merge masks, and we see where it sits in the pseudocode. Then split heads. This essentially takes your entire query key value vectors and splits them up into multiple attention heads. And then concat heads. So after you've done processing on each individual block of your query key and value, you have to merge them all together. That's the handle here in concatenate heads. And yeah, that's pretty much a task one. You'll be modifying these four files over here. Are there any questions? Okay, in that case, I'll give it to Michael, who'll talk about task two.
So, hello.
Yeah. Oh,
Okay, so just sorry.
yeah, four from this one.
Okay, hello. So task two is going to be basically combining all of these pieces into making a decoder-only architecture. The very first part that we're going to be talking about, though, is what types of things we're going to be passing in. So data preprocessing is our kind of goal for most of this task two. So what we're going to be doing is loading text as strings into memory, splitting strings up into tokens, building vocabulary dictionary to associate each vocabulary element with a numerical index, and then converting the text sequences into numerical indices. So these types of strategies would mainly be based off of like tokenization and stuff like that. What we'd be doing is we'd be grabbing character level tokenization, and we would be comparing what our tokenizations are with and making separate indices from it. Other ways of doing it is subword tokenizations, where we have different vocabulary sizes, and this is by having a massive corpus of data and where we can split off different subwords. And obviously, larger sizes mean take longer time and also usually are more accurate. One thing to write that is kind of it's more supposed to be talked about here is batching. So this is where you load your MP files, you tokenize your sequences with the provided tokenizer, then you add this golden, as stated here, shifted version of the start of the sequence, SOS token pre-appended, and a golden version of the end of sequence token appended. Please, please, please pre-append and append. I've seen a lot of students run into issues where they just forget to append or pre-append from past semesters. And then afterwards, you apply a custom collate function that pads the transcripts to the batch uniformly in length, providing lengths for mass generation and ensures proper tensor types. This is very helpful for when we're passing it into our decoder-only architecture. So let me go into the actual code. So in the code, this would be within our tokenizer. So this is where our code would be. So this is just like to read through. It's very important to read through this because you would kind of be needing it. And then, one sec. And then this is where you're going to be doing most of this loadings. Okay, back. So now talking about types of things we have to add to our decoder only is our positional encoding, where we make a we're just trying to get the respect of each of the elements from each other. How we do this is that we have a PT of I and PT of I plus 1, and we use basically like a Fourier domain to find what the differences are from like each of the elements. So now let me show you where that is in here. So that's going to be right here, positional encoding. So you have to implement the code that's in there here, and then mask. There's padding mask and causal mask. Causal mask basically says that you want to set true anything that you want to mask out, and maintain any set false anything that you don't want to mask out. And then padding mask, on the other hand, is just you set true whatever padding you're adding to your sequence length. So next, so now we have to add the sublayers that we have. So there's a couple of sublayers. There's a self-attention sublayer that we have to make. It should be here. So the self-attention, I would recommend looking through the notes and to understand what it's explicitly saying. The feed-forward network sublayer, which should be down here. One sec. Feed forward there. And then self-attention decoder. So this is where you're going to basically be making the whole layer from the sublayers, which, oops. And I believe this is, it might be on our transformers, one sec. It's self-attention, one sec, I'll just, it's in our transformers, okay. So it's in our transformers. So this is our decoder only transformer where we have this. And then lastly, we have our decoder only transformer. So this is our whole thing. And then now we have to figure out what our prediction is. So that's where our greedy search comes into play. So in your sequence generator, which would be is it homework? Yeah. Decoding. So this is where your sequence generator is. And this is where you're going to apply the greedy, generate greedy. Basically what it does is it grabs the probabilities of what your model predicts, and it picks the best probability, the maximum probability that it believes, and then it continues that until it reaches an EOS token. So that's whatever it states. So, and the LM trainer, that's the last part we have to implement, is where you kind of do all of the training processes. So it's you combine all of the decoder only architecture alongside this tokenization strategies, alongside predictions and stuff like that. Let me just show you where that is. So so it's right here. So this is where you combine all of your parts to finally get a metric on perplexity, which is like how uncertain your model is when it's predicting things. And you should get to get full credit on the homework assignment for task 2, you have to get a perplexity character of less than 3.5. And that is it for part 2. It's much shorter, but much longer when it comes to coding. So please reach out if you have any questions. Yeah, me too.
You guys want to use the laptop or?
I will say also, I will have 5-minute break before the PPT. So, for PPT.
Do you want? Did you? Okay.
I will write in the chat.
I'll say that right here. Guys, we're gonna have a 5-minute break between part 1 and part 2. So we'll meet you back in 9:35 EST. Oh, not 9:35. What? It says 9:35 here. 2:58 EST. Okay. I don't know why. I got lied to.
Doing the training part using the GPU compute that you need. So yeah, this is the main working directory structure. Like always, please make sure that you're using the same structure that's provided in the handout. And this is the data set structure. In part 1, you saw the decoder only transformer for causal language modeling. In part 2, we'll be moving on towards an encoder-decoder transformer. Okay, so for this homework, since you will be reusing most of the components, we recommend that you have like a private GitHub repository setup. so that it's easier for you to update your code and like keep reusing the same components. There are other processes, like you can have a Google Drive, but GitHub is the most simplest and easiest one. Yeah, and make sure it's a private GitHub repository and don't share your repositories. Okay, moving on to the main objective of this homework. Like I said, it's an encoder-decoder transformer to model a basic automatic speech recognition tasks. You will be given a subset of data that has filter banks, which are like speech features in filter banks, or like an MFCC form that can be extracted for the ASR task. Similar to part one, you'll use the start and the encode sequence encoding to make sure that the padding and the pad masks for the modeling tasks is same for all of the sequence lengths. Okay. Okay. Coming to the main task for the speech recognition, you have few data processing components, and then I'll move on to the training part. In the data processing components, you'll first load all the speech features in, we have like 80-dimensional filter banks, and then you'll normalize these features across all the recordings, and then you'll tokenize the transcripts, either character level or like subword level. And in subword level, you'll have, you can construct subtokens of different vocabulary sizes. We'll see to that later. And then you'll construct a vocabulary dictionary mapping for each numerical index, and then you'll convert the text transcripts into the numerical indices again. And you'll make sure that the speech features are aligned with the textual sequences so that it's proper for model training. And there's a tokenizer file that has some of the code structure. And like we mentioned, you can work with both either the character level or the subword level tokenization. In character level, you'll map each character towards a token. So with character level tokenization, you'll have longer token sequences, but it will have just a smaller vocabulary size. In subword level tokenization, you'll use byte-pair encoding based on whatever vocab size you want. We have three options here. You can either have 1,000, 5,000, or 10K characters. Just go through the tokenizer class and keep yourself familiar with the tokenize, encode, and decode methods that we have. And you will be given a local data set, and this is the data set structure. All the speech features are in NumPy format within the fbank subdirectory, and all the text transcripts are stored in NumPy format in the text subdirectory. Yeah, the data set is split already, and you'll first load all the NumPy files with the filter representations, and you'll load the corresponding transcription for the training data set. You'll tokenize all the transcriptions using the tokenizer class that we have already given you. And you'll apply any of these normalization strategies. We have three, the global MVN, the Cepstral, and none if you don't want to apply any normalization to these features. Then you can apply spec augmentation, either time masking or frequency masking for all the training data to make sure that you have a bigger data corpus. And then you'll prepare two versions of the tokenized script, either a shifted version and a global version with the start of sequence and the end of sequence token appended. You can track the data set statistics, like how many tokens, characters, and sequence lengths you have for your text corpus. And as always, you have a collate function for batching the data sequentially. And yeah, moving on to the model implementation part, most of the sub layers for this homework will be the same layers that you have already implemented in homework for part one. We recommend that you familiarize yourself with the multi-head attention class before you're implementing these sublayers. The layer that you'll be implementing here is the cross attention layer. And yeah, this is the diagram. All the colored components are all the reusable components from part 1. You'll be implementing a cross-attention decoder layer and a self-attention encoder layer for part 2. And in the encoder-decoder transformer, that's the transformer.py file, you'll be integrating all the components that you've already implemented. So yeah. Yeah, as usual, in the transformer layers, you have the speech embedding layer to process all these input features and uh, uh, apply the time reduction. You have the position encoding layer to inject positional information to both the input and the target embeddings. You will have a user-specified number of self-attention encoder layers to encode the input sequence, and the same for the cross-attention decoder layers to decode both the target and the encoder input. There is an embedding layer to convert the token into the target sequence based on the dimension vector, and a final linear layer followed by a lay norm and a dropout for regularization. Yeah, this is the transformer implementation part. And optionally, there's also a beam search decoding that you can experiment with. We provided the pseudocode for that here. Okay. Moving on to the training and the evaluation part. So the ASR trainer file is the main file where you will be managing both the training, validation, and the generation for the ASR model. Like most of the pseudocode is given. Just make sure that you follow the implementation instructions here carefully before implementing the file. For the baseline implementation, I think you need a cutoff of at least 50% CER. I think it's due on November 10th. Yeah, 31st, 21st. Okay. Okay, so I'll give a brief overview of some of the tips and tricks for this particular homework since it's very challenging. So first, make sure that you use the right tokenization strategy. Well, character level, the vocabulary size is small. There's longer sequences, and for subword tokenization, based on the size of the corpus that you're providing, it might take more time. So there needs to be a trade-off between the kind of strategies that you're implementing. And the 80-dimensional filter features that we are providing with the data set, you can experiment by dropping a few features to make sure that you're efficiently using the memory compute that you have, but don't drop too much information because that will also lead to like loss of critical information. And in the sequence of filter banks in the embedding layer are basically a few stacks of CNN and LSTMs. You can try downsampling the CNN layers and also the LSTMs to make sure that the training is more efficient and the inference speed is also like reasonably good. And there are a couple of training strategies which we will go into detail later. Uh, uh, yeah. And yeah, you can also try gradient accumulation, which is a technique that allows you to train models with large batch sizes when there's like limited memory constraints. This is already implemented for you. You can just use it through the config. There will be a couple of errors that you see that you might encounter in this homework. We've outlined a couple of steps to like debug it. you'll most probably encounter out of memory error. So make sure that you're following all these strategies properly. And for making sure that you're implementing the attention and the transformer layers properly, all of the runs that you do, it will all the attention plots and the sequences that you're trained will always be logged. So you can like go back and see your attention plots after you've trained it for a couple of epochs. So the decoder mask self-attention plot should look like this. It should be like diagonally dominant. Uh, so if it doesn't look like this, you're basically doing something wrong. And for the decoder cross attention mask, it should almost be a diagonal, but it won't be like a perfect diagonal because the sequence lengths vary. So just make sure that you're logging all your plots and track your epochs and see to that it's converging at some point. And as always, like please log all your runs on 1DB and track all your checkpoints. And yeah, we'll cover some of the training strategies and decoding strategies in detail now.
Yeah, okay. So now I'm going to introduce you 3 strategies to train this transformer model. So the first strategy is cold start. It's basically a very standard training process. And this is the only strategy that's provided in the student notebook. So if you just follow the student notebook, you can see the training process is also listed there. So yeah, it's here. So you can just follow the steps in the student notebook, then you can implement the first strategy very well. And except for the first strategy, because for homework part 2, we're going to train 2 parts of the model. The first part is the encoder, and the second part is the decoder. And since we all know that we already trained a decoder in our homework 4 part 1, right? So in homework 4 part 2, we can utilize the decoder that we trained in the homework part 1. So this is the basic concept of the strategy. Second, which is pre-trained decoder initialized. So you're gonna basically use your, okay, maybe I need to make this bigger for everyone to see it. Okay. Okay, so the concept would be use the decoder model that you trained in homework 4 part 1 and utilize it in homework 4 part 2. So the basic, there are several advantages for this. So it's going to speed up convergence, and it's also going to improve models' performance by leveraging prior knowledge from a pre-trained language model. And here's the several steps that you need to follow. The first one is that you need to initialize with the pre-trained weights. It's like in your homework 4 part 1, you already get the PTH file of the decoder, then you download it, then you upload to the path where you are training homework 4 part 2, then you need to load the checkpoints from homework 4 part 1 to finish this initialize pre-trained weights. And then the second step is that you need to freeze the pre-trained weights. So initially you will freeze the pre-trained weights of the decoder and train only the encoder and cross attention layers on the ASR task. So this ensures that pre-trained decoder weights are not modified during the early stages of training. And the last step is to unfreeze and fine-tune the whole model together. So in the last step, you're going to unfreeze the decoder that you trained in homework 4 part 1. So in this stage, the weights of decoder and encoder is going to be updated at the same time. Okay, so for strategy second implementation, this is not provided in the notebook, but here are some resources that you could use, and it's included in the handout. So you can use the from pre-trained decoder method, and you can also use the create optimizer function. Yeah, so here's the tips for this method, which is because you are using the decoder trained from homework 4 part 1. So you need to make sure that the settings or the config or the structure of your model that you set from homework 4 part 1 is aligned with what you want in homework 4 part 2. Otherwise, when you load the previous checkpoint, there will be some problem. Yeah, and also except for the model structure, you also make sure you use the same tokenizer and same dimensionality. Yeah. So the third strategy is progressive trainer. So progressive trainer, its concept is basically you're going to train the model gradually. You will increase the model's capacity during training, when the training epoch is increasing. So here's some advantage for this strategy. You're going to reduce the risk of overfitting early in the training process. And this could also speed up the initial stages of training by using fewer parameters, which will also cause faster convergence. So this concept is basically you're gonna gradually increase the difficulty for this model. So how are we gonna define the concept of difficulty? So there are different concepts from difficulty. So the first one is you're gonna scale up the data set. And the second one is increase the model complexity. And the third one is adjusting regularization techniques such as augmentations, dropout, or label smoothing. Because maybe at first you're gonna set the dropout rate to very slow, to very small. So the model, it is easier for the model to learn the features, right? And maybe gradually you can increase a little bit of the dropout rate. So to make it more difficult for the model to learn the features. Okay, so I'm gonna also introduce the schedule for increasing difficulty. So there are different ways to schedule this. So the first one is fixed schedule. You can like progressively double the number of decoder and encoder layers for every 5 epochs. And you can also simultaneously increase regularization as the epochs is increasing. And the second schedule method is more sophisticated. Like you can incorporate self-paced learning. So the pace could be dynamically adapted to the training performance. So here's the recommended schedule. I can zoom in this a little bit. So the first is that you need to start small. Like you can begin training with a minimum architecture, like with only one encoder layer and one decoder layer. And then you're gonna progressively add the layers. Like after each pre-training iteration, you can increase the number of layers in the decoder and encoder. So it'll make the model progressively deeper. So this allows the model to gradually learn more complex features without overwhelming it early on. And later you're gonna freeze the previous layers that you trained. So you can freeze the previous added layers to prevent them from being updated in the early stages of training. And you're also gonna increase the regularization, like dropout and label smoothing. And after all of this, you're gonna unfreeze all the layers to train all the layers together. Okay, so here we can see an example. Like initial stage, there's only one layer for decoder and encoder. So this is relatively a small and a simple model. And there's no freezing or regularization is applied. You can just imagine the dropout rate is 0, okay? And it uses 20% of the training data. And the second stage is that you increase the encoder and decoder layer into 2. So there are gonna be 2 encoder layers and 2 decoder layers. And you're gonna freeze the previous layers as well. And there's also no regularization because this stage is also relatively early and you don't want to overwhelm the simple model. Okay, and then you can still add on more layers on top of the original model. The third stage, you can use 4 layers for both encoder and decoder, and you're going to freeze the previous layers. And right now, since the model has learned some features, so you can add some dropout rate and label smoothing. Okay, and after all of this, you have gone through 3 stages. And right now you're gonna unfreeze all the 6 layers. And you're gonna train all the 6 layers at the same time. So right now, for the regularization, you can set the dropout rate larger and label smoothing to 0. And yeah, it's basically like this. And for the implementation, you're also gonna implement this by yourself. It's not provided in the notebook, but here are also some resources that you can use, and you can find them in the handout. Okay, and there's another note, which is you can actually combine the strategy 2 and 3 together. Yeah. Okay, I think that's all for the strategy part. Yeah.
That document will be shared.
Oh, this document is also contained in the write-up. You can find it in the write-up.
Yes.
Yeah.
Yeah, great. Yeah, so for now yeah, we've explained about some different strategies that we can use for training our ASR model. And now we're going to move on to the inference part. So yeah, assuming that you guys have basically implemented those training mechanisms and successfully trained your model, then you're gonna run the inference part, which is relatively simple than the previous stages, but there's a few. Oh yeah, thank you. Right, but there are a few like important parts that you have to make sure to apply during the inference. So you have to pass this recognition config during your inference, which is also, and the purpose of this is to use this trainer.recognize function, this model, which you will be implementing in the homework 4 library, which is provided in our handout. And the specifics of each components, the num batches, or just your like batches that you're using, and the temperature and repeat penalty and this beam width, these are the parameters that are beam search specific. So the especially the repeat penalty is the penalty that you're giving to the beam search, whether you're repeating where you penalize the repeating beams during your beam search, and the beam width is definitely the number of beams that you're using during beam search. And one thing that you guys should notice is if beam width is set to 1, it is equivalent to greedy search. And if you use larger beam width, then they will during the inference time that like the amount of compute that it is required, it gets like exponentially larger. So and this actually depends on not only on the width size, but also on the entire sequence size. So you guys should note that if you're using like character level tokenization that we explained earlier, those specific tokenizations result into longer sequence length, which is definitely not very, the entire beam search time gets exponentially longer if you use like character level tokenization. So for those tokenization methods, you should use less beam width, maybe like 1 or like 2 or 3. But this actually would differ based on which compute you're using. So as long as your compute allows to increase beam width, you can explore on various beam width. And the LM weight and LM model are the specific parameters that are used for shallow fusion method, which is another amazing part that we can leverage the decoder only model that is trained for homework 4 part 1. So on the training methods that we explored so far is more like a deep fusion strategy where you actually leverage the decoder only model and then integrate to our encoder-decoder model to further train on those and merge those model and then further train it. But here we're only merging the pre-trained decoder only model in our inference stage. So yeah, and the specific libraries are also you're going to implement it, whether it is optional, but it is like recommended for you guys to explore it as well. So you're gonna implement it in the recognize module and the ASR trainer model. And this ln weight is for weighting the amount of fusion you're gonna apply to the pre-trained model, and you're gonna linearly combine those prediction outputs to your the model that you're training throughout these ASR training tasks. And this LM model is a specific model that you're gonna pass through, which is pre-trained decoder model. Decoder only model, yeah. And then after that, you just specify the config name, and then you're gonna pass through these config into the trainer.recognize, and then you're gonna see the results. And yeah, you're gonna further process. You shouldn't actually modify this cell, this part, and it will create a results.csv file, which you're gonna submit through Kaggle. And yeah, after that, you're gonna generate this model.metadata and the entire zip file that is required for final submission of your code, which is due 48 hours after the Kaggle submission date. And yeah, so this is basically the same as the previous homeworks, except you also have to include the homework 4 library components within the zip file, which is also actually set in this code, which you're gonna add here. Yeah, and along this, like you should ensure all of these materials are included in the final submission code zip file. And yeah, that'll be all for the this homework 4 part 2 task. And yeah, just notifying again, the deadline of the checkpoint would be November 21st, the end of November 21st. And the on-time final submission deadline would be December 5th. And please note that your parameter limits are 30 million for both part 1 and part 2. And you shouldn't use any pre-trained model on this homework as usual. So if you like don't stick on these then well, you guys won't be able to get like full credits. So please keep those in mind. And the Slack submission deadline is until December 11th, end of December 11th. So if you have like Slack days left and you want to use it, you can use it until this date. Yeah. And I think that's all. And do you have any questions regarding, yeah.
You said the LM model is a pre-trained one that you pass on, but that's from part 1.
Yeah, that's the model that you've pre-trained in the part 1. So that won't be considered as the pre-trained model that I'm mentioning here. Yeah. All right. Oh, and by the way, I should actually notify that during shallow fusion, you have to use a compatible LM model where all those like layer dimensions and tokenization strategies match with the current training config that you're using. So you have to ensure that before you're applying either deep fusion or shallow fusion. Yeah. Are there any other questions? All right, cool. Thank you so much for attending today. Thank you.
By the way, the pizza is here.
Yeah.
Yeah. So should we stop the, okay.
So the location for the class is in gate 5